In residential electrical services, particularly in rural areas with pole-mounted services, understanding the distinction between service conductors and feeders is crucial. When the utility provides power to a meter disconnect, typically within 150 feet, the responsibility shifts to the homeowner. The conductors running underground from the meter main to the house are classified as feeders. According to the National Electrical Code, a service lateral is an unfused conductor from the utility to the service equipment. Service entrance conductors, on the other hand, are the supply conductors between the point of connection to the service drop or service lateral conductors and the service equipment. Therefore, the conductors emerging from the meter main and running underground to the house function as feeders, establishing the meter main as the main disconnect. The main service disconnect, as specified in NEC section 230.70, must be located either inside the building at the nearest point of entrance of the service conductors or outside the building on or within sight of the building. In situations where the meter main serves as the main disconnect, running conductors underground to the house and into the panel is acceptable. Section 230.70a, on which emphasizes keeping conductors as short as possible and inside nearest the point of entrance of the service conductors, becomes less relevant because the system is already fused at the pole. The readily accessible location of the main disconnect is a critical aspect. The electrical codes generally require it to be within sight of the house. A situation where a pole-mounted meter main is 700 feet away from the house, with only the top of the house visible due to terrain, does not meet the requirement of being within sight. Furthermore, the wiring configuration of a 3-wire underground system with the ground and neutral bonded at the panel inside the house, lacking additional grounding paths back to the meter, is non-compliant. When powering an additional building from the same service, the conductors leaving the first building are treated as feeders, and upon arrival at the second building, they become service entrance conductors terminated in service equipment. This mirrors the situation where if a panel inside the house has a main disconnect and is located at the closest point to the service conductors, bonding the neutrals and grounds together, that panel may seem appropriate. However, the meter main should be within sight of the building, and the neutral and ground should not be bonded at the panel in the house. Instead, a proper grounding electrode system must be installed and connected to the neutral at the service equipment, typically the meter main. Grounding electrode system, or GES, is a system that connects the electrical system to the earth, providing a path for fault current to flow back to the source. This system typically includes a grounding electrode, such as a ground rod, ground plate, or metal water pipe, and a grounding electrode conductor that connects the electrode to the neutral busbar in the service equipment. The purpose of a grounding electrode system is to stabilize the voltage to ground during normal operation and to provide a low impedance path for fault current to flow back to the source during a fault. This helps to protect people and equipment from electrical shock and damage. Now, let's dive into the National Electrical Code, or NEC, and further understand this. The NEC is a set of standards and guidelines for safe electrical installations. It is updated every 3 years and is used by electricians, inspectors, and engineers to ensure that electrical systems are installed safely and correctly. Here are some key NEC articles related to grounding and bonding. Firstly, Article 250 covers the requirements for grounding and bonding electrical systems. It includes information on grounding electrodes, grounding electrode conductors, equipment grounding conductors, and bonding jumpers. Secondly, Article 230 covers the requirements for service entrances, including the location of the service disconnect, the size of the service conductors, and the grounding requirements. Thirdly, Article 300 covers the general requirements for wiring methods, including the types of cables and conductors that can be used, the methods for installing them, and the requirements for protecting them from damage. Fourthly, Article 310 covers the requirements for conductors, including the ampacity of conductors, the types of insulation that can be used, and the requirements for derriting conductors in certain conditions. Fifthly, Article 408 covers the requirements for switchboards and panel boards, including the requirements for grounding and bonding, the overcurrent protection requirements, and the requirements for labeling. Now, let's review some of the key grounding and bonding requirements of the NEC. Firstly, all electrical systems must be grounded to provide a path for fault current to flow back to the source. Secondly, the grounding electrode system must be installed in accordance with NEC Article 250. Thirdly, the equipment grounding conductor must be sized in accordance with NEC Table 250.122. Fourthly, bonding jumpers must be used to connect all metal enclosures and equipment together. Fifthly, the neutral conductor must be bonded to the grounding electrode system at the service equipment. Sixthly, the grounding electrode conductor must be sized in accordance with NEC Table 250.66. Seventhly, all splices in grounding conductors must be made using listed connectors. Eighthly, grounding conductors must be protected from physical damage. Ninthly, grounding electrodes must be located as close as practicable to the service equipment. Tenthly, grounding electrodes must be installed below the permanent moisture level, if practicable. Now let's review NEC 230.70, which pertains to the location of the service disconnecting means, which is essential for ensuring electrical safety. This section outlines the requirements for where the main disconnect switch must be placed in a building's electrical system, and it's vital for electricians and inspectors to adhere to these guidelines to prevent electrical hazards. NEC 230.70A focuses on the service disconnecting means location, stating that it should be installed at a readily accessible location either inside the building nearest the point of entrance of the service conductors or immediately outside the building. The primary aim of this requirement is to allow for quick and easy access to disconnect power in case of emergencies such as fires or electrical faults. The term readily accessible is defined in the NEC as being capable of being reached quickly for operation, renewal, or inspections, without requiring those to whom ready access is requisite to climb over or remove obstacles or to resort to portable ladders, and so forth. This means the disconnect must be easily reachable without any obstructions that could hinder its use. The phrase nearest the point of entrance is also crucial. It means that the disconnect should be as close as possible to where the service conductors enter the building. This reduces the length of unprotected conductors inside the building, minimizing potential hazards. There are exceptions to this rule, particularly in large buildings where it might not be practical to have the disconnect right at the point of entry. In such cases, the disconnect can be located elsewhere, provided it is still readily accessible. NEC 230.70 ATWO addresses a separate building or structure provision. If a building or structure is supplied by a feeder or branch circuit from another building, the disconnecting means for that building or structure must be installed either inside or outside at a readily accessible location nearest the point of entrance of the conductors. This ensures that each building has its own disconnect, allowing for localized power shutoff. NEC 230.70 A3 covers 1 and 2 family dwellings. For these types of dwellings, the service disconnecting means must be installed at a readily accessible location either inside the building nearest the point of entrance of the service conductors or outside the building. This is similar to the general rule, but emphasizes the importance of accessibility in residential settings. NEC 230.70B discusses the marking requirements for the service disconnecting means. Each service disconnect must be permanently marked to identify it as a service disconnect. This marking must be legible and durable to withstand environmental conditions. This ensures that anyone working on the electrical system can easily identify the main disconnect switch. NEC 230.70C covers the height requirements for the service disconnecting means. The operating handle of the disconnect switch must be installed so that it is not more than 6 feet 7 inches above the floor or working platform. This height restriction ensures that the disconnect is accessible to most people, including those with disabilities. NEC 230.70D addresses the remote control. In some situations, it might be necessary to control the service disconnect remotely. If a remote control device is used, it must be located at a readily accessible location and must be clearly labeled to indicate its function. This allows for safer and convenient operation of the disconnect from a distance. NEC 230.70E covers the rating of the disconnecting means. The service disconnecting means must have a rating sufficient to carry the calculated load. This ensures that the disconnect can handle the maximum current that the electrical system is likely to draw. NEC 230.70F discusses the grouping of disconnecting means. If a building has multiple services, all the service disconnecting means must be grouped together in one location. This makes it easier to shut off all power to the building in an emergency. Now let's talk about grounding electrode systems. Grounding electrode systems are essential for electrical safety, providing a low impedance path for fault currents to return to the source, thereby minimizing the risk of electric shock and equipment damage. According to the NEC, specifically Article 250, a grounding electrode system must consist of one or more of the following electrodes. Firstly, a metal underground water pipe that is in direct contact with the earth for at least 10 feet. This pipe must be electrically continuous and free from any insulating coatings or joints that could interrupt the electrical connection. Secondly, a ground ring encircling the building or structure, buried directly in the earth at a depth of not less than 2.5 feet. The ground ring must be made of bare copper conductor not smaller than 2 AWG. Thirdly, a concrete encased electrode consisting of at least 20 feet of bare copper conductor not smaller than 4 AWG encased in at least 2 inches of concrete. This electrode is typically installed in the footing or foundation of a building. Fourthly, a ground rod or pipe electrode driven into the earth. The rod or pipe must be at least 8 feet in length and must be made of galvanized steel, copper, or other suitable material. The rod or pipe must be driven into the earth to a depth of at least 8 feet, and it must be located at least 6 feet away from any other grounding electrode. Fifthly, a plate electrode buried in the earth. The plate must be made of copper, iron, or steel and must have a surface area of at least 2 square feet. The plate must be buried at a depth of at least 2.5 feet. In addition to these electrodes, the NEC also permits the use of other grounding electrodes such as metal building frames and other effectively grounded metal structures. However, these electrodes must meet specific requirements to ensure their effectiveness. The grounding electrode system must be connected to the service equipment enclosure and to the neutral conductor at the service entrance. This connection is made using a grounding electrode conductor, which must be sized according to NEC Table 250.66. The grounding electrode conductor must be securely fastened to the grounding electrode and to the service equipment enclosure. It must also be protected from physical damage. In situations where multiple grounding electrodes are used, they must be bonded together to form a single grounding electrode system. This bonding is typically accomplished using bonding jumpers, which must be sized according to NEC Table 250.102. The bonding jumpers must be securely fastened to the grounding electrodes and to each other. In addition to the grounding electrode system, the NEC also requires the installation of equipment grounding conductors. Equipment grounding conductors are used to ground non-current carrying metal parts of electrical equipment such as enclosures, raceways, and appliance frames. These conductors provide a low impedance path for fault currents to return to the source, thereby minimizing the risk of electric shock. The equipment grounding conductor must be sized according to NEC Table 250.122. It must be securely fastened to the equipment enclosure and to the grounding electrode system. It must also be protected from physical damage. In summary, a grounding electrode system is a critical component of any electrical system. It provides a low impedance path for fault currents to return to the source, thereby minimizing the risk of electric shock and equipment damage. The grounding electrode system must consist of one or more of the electrodes specified in the NEC, and it must be connected to the service equipment enclosure and to the neutral conductor at the service entrance. Now, let's review a bit about bonding. Bonding is another critical aspect of electrical safety. Bonding ensures that all metal parts of an electrical system are electrically connected, creating a low impedance path for fault currents to flow back to the source. This helps to minimize the risk of electric shock and equipment damage. According to the NEC, specifically Article 250, bonding is required for all metal parts of an electrical system that are likely to become energized. This includes metal enclosures, raceways, equipment frames, and other metal parts. Bonding is typically accomplished using bonding jumpers, which are conductors that connect the metal parts together. The bonding jumpers must be sized according to NEC Table 250.102. They must be securely fastened to the metal parts and must be protected from physical damage. In addition to bonding the metal parts of an electrical system together, the NEC also requires bonding the neutral conductor to the grounding electrode system at the service entrance. This bonding connection ensures that the neutral conductor is at the same potential as the earth, which helps to stabilize the voltage to ground and minimize the risk of electric shock. The bonding connection between the neutral conductor and the grounding electrode system must be made using a bonding jumper that is sized according to NEC Table 250.66. The bonding jumper must be securely fastened to the neutral conductor and to the grounding electrode system. It must also be protected from physical damage. In summary, bonding is an essential aspect of electrical safety. It ensures that all metal parts of an electrical system are electrically connected, creating a low impedance path for fault currents to flow back to the source. Bonding is required for all metal parts of an electrical system that are likely to become energized, and it must be accomplished using bonding jumpers that are sized according to NEC Table 250.102. The neutral conductor must also be bonded to the grounding electrode system at the service entrance, using a bonding jumper that is sized according to NEC Table 250.66. Proper grounding and bonding are essential for electrical safety. By following the requirements of the NEC, electricians and homeowners can ensure that electrical systems are installed safely and correctly, minimizing the risk of electric shock and equipment damage. In the scenario described earlier, the wiring in the friend's house is not compliant with the NEC. The meter main should be within sight of the building, and the neutral and ground should not be bonded at the panel in the house. A proper grounding electrode system should be installed to provide a safe and effective path to ground.